Deep in the cosmic darkness lies IC 1011, a galaxy so massive it seems to devour others whole. What forces shaped this colossal giant, and how many galaxies has it consumed? Tonight we'll journey into its luminous heart. If you enjoy exploring the mysteries of the universe, please like, subscribe, and share, and tell us in the comments, do you think there's a limit to how big a galaxy can grow? Thank you for watching. Far beyond the luminous spiral arms of the Milky Way, past the faint edges of known galactic clusters, lies a domain of distance and silence, where scale begins to lose meaning. In this remote part of the cosmos, light travels for more than 1 billion years before reaching human instruments. Space there is not empty but filled with a thin glow of ancient radiation and drifting particles, the residual hum of the universe's earliest moment. Through powerful telescopes, this deep expanse appears as a faint weave of light and shadow, a cosmic fabric where galaxies are no longer isolated islands, but threads woven into a larger pattern. Within this web, gravity is the unseen architect, drawing together knots of matter so massive that they reshape the space around them. One of these knots is the AEL 2029 cluster, a colossal gathering of galaxies bound together across millions of light years. From Earth's perspective, it is only a small glimmer on the vast celestial map, yet in reality, it contains more stars than can be imagined, each one a sun within a crowded cosmic city. The light that reaches observers today left that cluster when multicellular life was only beginning to flourish on Earth. What humans now see is not the present, but a frozen image of the distant past, captured in the long delay of light. At this range, familiar galactic shapes begin to dissolve. Spiral arms, barred cores, and dusty lanes blur into diffuse smudges of brightness. The deeper one looks, the more galaxies seem to merge into one another, their boundaries uncertain, their forms softened by time and distance. Between them lies a medium of superheated gas, tenuous, invisible to the eye, but glowing in X-ray wavelengths. This plasma fills the cluster like an ocean of energy, its temperature reaching tens of millions of degrees. Within it, galaxies move as though swimming through a hot, transparent sea, slowed by friction so faint it would never be felt in a human context. This environment is inhospitable to new creation. Gas that might form stars is stripped away, heated and dispersed, leaving the cluster bathed in old light from ancient stellar generation. Through long observation, astronomers have learned that these vast clusters are among the most stable structures in the cosmos. Their size and mass make them resistant to external change. Yet, even stability has a cost. Over billions of years, their inner galaxies are drawn inward, colliding and merging until only a few giants remain at the core. It is here, at the gravitational center of EL 2029, that a single extraordinary galaxy dominates all others. From this great distance, its glow is subtle but steady, a haze of golden light, diffused across millions of light years. To call it a galaxy is to simplify something that stretches the very limits of definition. Its outer envelope fades so gradually that astronomers cannot precisely say where it ends. Its mass rivals that of thousands of Milky Ways combined, and its radius extends far beyond what human eyes can imagine as a coherent system. The light from IC 1011 is ancient, its photons scattered and redshifted by the expanding universe. Observed through ground-based telescopes, it appears as an elongated blur, soft-edged, without the graceful arms of a spiral. Its core burns with concentrated brilliance, surrounded by a faint halo-like diffusion. The color is pale gold, the hue of old stars, each of those stars individually too faint to distinguish, contributes to the collective radiance that marks the galaxy's presence against the darkness. If seen up close, those same stars would fill the sky more densely than any field of view from Earth. Yet the vast majority of IC 1011's light is diffuse, stretched into an almost imperceptible gradient that fades into the cluster's ambient glow. Beyond the visual image lies the gravitational truth. IC 1011's mass warps the motions of everything near it. Smaller galaxies fall into its domain, slowed and absorbed by the relentless pull of its center. The cluster itself is drawn inward, its entire structure subtly rearranged by this gravitational monarch. This process is not violent in a human sense. It is patient, stretching over hundreds of millions of years. In the scale of cosmic time, the galaxy behaves like a slow tide, eroding and consuming whatever drifts too near. To observe such a system is to witness a history of accretion written across light years, a silent record of growth through merger and absorption. In the greater context of the universe, IC 1011 occupies a position of rare distinction. It represents one of the largest and most luminous elliptical galaxies known to science. Where typical galaxies may contain a few 100 billion stars, this one holds trillions. Its dimensions span several million light years, enough to engulf the Milky Way and Andromeda side by side, along with countless smaller galaxies. Even so, its light is faint when spread across such an immense area. Only through sensitive instruments can its full extent be traced, revealing a shape that blends seamlessly into the diffuse glow of the surrounding cluster. This gradual transition between galaxy and cluster environment blurs the very concept of boundary. In IC 1011, galaxy and cluster are nearly one continuum, the individual lost in the collective. This vastness invites reflection not of meaning, but of proportion. The human mind, evolved to perceive only local scales of mountains and oceans, cannot easily grasp a structure so large that its light takes millions of years merely to cross itself. Yet the instruments that detect its faint signals transform these distant photons into measurable data, into brightness profiles and velocity curves. From them emerges a picture of the galaxy's immense density, its distribution of mass, and the ghostly halo of stars that surrounds it. These observations form the basis of all that is known about IC 1011. They describe a place where gravity, over cosmic ages, has drawn matter into the most complete expression of galactic growth known in the universe. Around it, the rest of the Able 2029 cluster forms a supporting background, hundreds of galaxies of varying size, each with its own stars and histories. Some are still intact, moving in long elliptical orbits. Others are already falling inward, stretched into luminous trails as they are stripped of their outer layers. In the cluster center, IC 1011 absorbs these remnants like a slow-moving storm, drawing in clouds. The space surrounding it is littered with the debris of this process. Stellar streams, faint arcs of disrupted light, and faint X-ray echoes from heated gas. Together they form a halo that extends farther than any individual galaxy's gravitational reach, creating an impression not of a single structure, but of a gravitational landscape sculpted by time. The immense light of IC 1011 remains suspended in the heart of the cluster, its diffuse glow blending with the surrounding haze of intergalactic stars. Every particle of dust, every isolated sun, moves in slow response to gravity's pull, shaping a pattern that endures across billions of years. The airless void between its stars holds no sound only the silent drift of radiation and time. Around it, the cluster continues to shimmer faintly through the X-ray fog, an ocean of heat and motion so vast that distance itself seems to blur. In this remote region of space, scale overwhelms imagination, and light alone records the quiet balance between matter and gravity that defines the galaxy's form. The Able 2029 cluster lies more than 1 billion light-years from Earth, a city of galaxies bound together by the invisible gravity of dark matter. To the instruments that study it, the cluster is not a place of emptiness, but of structure, an organized system that stretches across space for millions of light years. Within this immense volume, hundreds of galaxies move in slow orbits around a shared center of mass, their trajectory shaped by the combined influence of all the matter that is gathered here over cosmic time. Between these galaxies is not the dark void of empty space, but a vast medium of hot plasma, thin yet pervasive, glowing faintly in X-ray wavelength. This intra-cluster medium forms the atmosphere of the cluster, an ocean of charged particles so rarefied that a cubic meter would contain fewer atoms than the best vacuum created on Earth. Yet on the scale of the cluster, its total mass outweighs that of all the stars combined. It is a component as essential as the galaxies themselves, a reservoir of energy and radiation that reveals the true dimensions of this cosmic metropolis. Seen through optical telescopes, Able 2029 appears as a diffuse concentration of light. Each pinpoint is a galaxy, each galaxy a collection of billions of stars. The brighter members cluster near the center, drawn inward by the enormous gravitational potential. Fainter ones linger at the periphery, their orbits stretched and slowed by time. In between, streaks of light mark the remnants of collisions, the faint tidal arcs that trace where smaller systems have been torn apart and absorbed. The cluster is dynamic yet slow, every motion taking hundreds of millions of years to unfold. Its structure is roughly spherical, with the densest concentration at the core, where IC 1011 resides, like the central district of a luminous city. The galaxies there are packed so closely that their halos overlap, merging their light into a continuous background. From afar, this central region glows more brightly than the outskirts, a sign of the cluster's deep gravitational well. The environment within Able 20, the plasma that fills its space, reaches temperatures of tens of millions of degrees Celsius, emitting powerful X-rays detected by space-based observatories. These emissions reveal the cluster's total mass and the distribution of its dark matter halo. Though the gas is thin, its heat is immense, the result of gravitational compression as material fell into the cluster during its formation. The pressure of this hot medium prevents new gas from cooling and collapsing into stars, which is why clusters like this one are largely composed of old galaxies, their star-forming days long past. The galaxies that move through this medium are stripped of their own gas, leaving them barren and reddish. In this way, the cluster gradually suppresses the birth of new stars, transforming its members into relics of earlier, more active times. The light that escapes from Able 2029 carries the signatures of its past. The redshift of its galaxies tells of cosmic expansion, stretching their emitted wavelengths as the universe itself grows gauge. By measuring this redshift, astronomers can determine not only distance, but also the cluster's motion through space. It drifts within a vast network of filaments and voids known as the cosmic web, connected to other clusters by tendrils of dark matter and diffuse gas. These filaments act as highways of cosmic material, channeling galaxies and matter toward the densest nodes. Over billions of years, AL 2029 has grown by drawing in smaller groups from its surroundings, a process still continuing in the faint outskirts where galaxies approach along invisible bridges of gravity. The density of galaxies within the cluster produces a phenomenon known as gravitational lensing. Light passing near the cluster is bent by its immense mass, distorting the appearance of more distant galaxies behind it. Observed carefully, these distortions reveal the invisible distribution of dark matter that holds the cluster together. Maps constructed from lensing measurements show that the visible galaxies represent only a fraction of the total light. The rest is composed of matter that does not emit or absorb light, detectable only through its gravitational influence. This dark matter halo extends far beyond the luminous boundary of the cluster, shaping the motions of its members and stabilizing its structure against the outward push of cosmic expansion. Within this gravitational field, IC 1011 dominates. It lies at the cluster's center, where the potential is deepest. Around it, the other galaxies move like satellites around a massive sun, each following an orbit defined by the collective gravity of billions of solar masses. Some will eventually spiral inward and merge with the giant, contributing their stars to its already immense body. Others will escape, flung outward by gravitational interactions to drift at the edges of the cluster or beyond. These exchanges are slow and balanced, part of the long equilibrium that defines such colossal systems. Every merger adds new energy to the intra-cluster medium, heating the gas further and enriching it with heavier elements forged in ancient stars. Over time, the cluster becomes a vast repository of cosmic memory, containing within its particles the remnants of countless generations of stellar life and death. If one could watch the AEL 2029 cluster over billions of years, its appearance would change only subtly. Galaxies would drift and merge, their shapes deforming as gravity pulled them together. The core would become brighter and smoother, the outskirts dimmer as material settled inward. Eventually, nearly all its members might coalesce into a few central giants surrounded by a halo of faint light. This slow evolution is a natural outcome of cosmic gravity acting over great time. In this sense, the cluster is both ancient and alive, still reshaping itself, though on a scale far beyond human perception. The radiation it emits reaches Earth as a faint signal, barely detectable without sensitive instrument. Yet from these signals, astronomers can reconstruct the entire architecture of the cluster, its size, temperature, and density profile. They can trace the contours of its gravitational potential and measure the total mass contained within. These observations transform what appears as a tiny speck of light in the sky into a detailed physical system governed by the same laws that shape the Milky Way. The scale is greater, but the principles are universal. The light behaves according to the same physics, the same constants, the same gravity that holds the solar system together. In this way, ABLE 2029 connects the human scale to the cosmic one, bridging the vast gulf between observation and the reality it represents. At the cluster's periphery, faint galaxies continue to fall inward, remnants of smaller groups drawn along the gravitational filaments. Their entry adds subtle motion to the cluster's halo, creating weak ripples in the hot gas that slowly dissipate as heat. These infall events will continue far into the future, ensuring that ABLE 2029 grows ever more massive, even as the wider universe expands. Over immense time, the cosmic web that feeds it will stretch and thin, leaving the cluster increasingly isolated. But within its boundaries, gravity will still dominate, binding its stars, its gas, and its dark matter into a coherent whole. In this city of galaxies, each component, light, gas, dark matter, plays its part in maintaining balance. The galaxies drift through the plasma like silent ships, their paths bending in slow arcs under the influence of forces unseen. The hot medium glows with the energy of ancient collapse, a reminder of the violence that once shaped the cluster's birth. The dark matter halo, though invisible, provides the structure that holds all of it together. In combination, they form one of the universe's grandest architectures, a monument of gravity that endures through ages, preserving the faint light of countless stars within a single bound domain. When IC 1011 first entered the records of astronomy, it appeared as nothing more than a faint, featureless patch of light against the deep field of Abel. Its recognition began not with a dramatic revelation, but through the quiet accumulation of photographic plates in the mid-20th century. Astronomers examining the cluster through large optical telescopes noticed an unusual glow at its center, broader and more diffuse than that of neighboring galaxies. At first, it was difficult to define its shape or bound. The galaxy's light extended so far that its edges blended into the background brightness of the cluster itself, leaving observers uncertain where the galaxy ended and the surrounding space began. Only by comparing multiple exposures taken with longer integration times did they realize that the central haze was not a product of instrument or atmosphere, but an object of extraordinary size. The deeper the exposure, the larger the galaxy seemed to grow, its outer regions faint but persistent. It became clear that this was no ordinary elliptical galaxy. It exceeded in scale even the brightest central galaxies known in other clusters, such as those in Coma or Perseus. The name IC 1011, derived from the Index Catalog of Nebulae, carried little of its majesty, but it marked the formal recognition of one of the largest individual structures ever identified. As instrumentation improved, astronomers began to measure its light more precisely. Photometric studies revealed a smooth gradient of brightness that followed the characteristic profile of elliptical galaxies, but extended far beyond typical limits. While the Milky Way's light falls to invisibility within a few tens of thousands of light years, IC 1011's halo stretched across several million. The outer regions were so dim that only careful background subtraction could reveal them. In those faint outskirts lay the key to its nature, the remnants of countless mergers, stars flung outward during collisions that had long since faded from memory. Each faint point represented an orbiting fragment of some former galaxy, now absorbed into the whole. This recognition transformed the earlier assumption of a simple, isolated structure into the understanding of a living record of cosmic accumulation. Spectroscopic data followed, giving the galaxy a redshift value that placed it at a distance of more than 1 billion light years. That measurement confirmed what the eye could not grasp. The faintness of its glow was not only the result of low surface brightness, but also of immense distance. Its total luminosity, corrected for that distance, placed it among the most radiant galaxies ever measured. Yet despite its brilliance, its color told another story. It was dominated by yellow and red tones, the signature of old stellar populations. Young blue stars were almost absent. This spectral quietness implied an ancient system long past the turbulent phase of star formation. The galaxy's light was steady, unchanging, a glow of accumulated age. With the arrival of digital detectors and space-based imaging, the structure of IC 1011 became clearer. High-resolution images showed a smooth elliptical form without spiral arms, dust lanes, or irregularities. Its core was dense and bright, but unlike active galaxies, it displayed no strong jets or emission lines. There was no sign of recent interaction vigorous enough to disturb its shape. Its surface brightness declined gently outward, suggesting that it had reached a state of near equilibrium after countless mergers and relaxations. This calm appearance, paradoxically, was the product of extreme history. The more chaotic its past had been, the smoother it appeared in the present. Every collision had erased the sharp features of the galaxies that came before, blending their stars into a homogeneous whole. As astronomers refined their measurements, they faced a problem of scale. When defining the size of a galaxy, one must choose where its light effectively ends. For ordinary systems, that boundary can be drawn with precision, but in IC 1011, the light fades so gradually that any limit seems arbitrary. Estimates of its diameter vary depending on how faint a contour is chosen. Some measure it at about 500,000 light-years across. Others, tracing the light to its furthest detectable reach, claim several million. Either way, it surpasses all familiar examples. Its sheer extent challenges the very language used to describe galaxies. It is not a single island of stars, but a diffuse continent, a gradient of starlight merging seamlessly with the intra-cluster medium. The first systematic studies of IC 1011's brightness distribution revealed another peculiarity: the presence of a large, low-density halo beyond the central bulge. In other galaxies, such halos are often evidence of tidal debris or the cumulative result of minor mergers. Here, the halo alone outshines entire galaxies, implying a history of large-scale cannibalism. The concept of a seedy galaxy, a central dominant galaxy with an extended envelope, was developed to describe such objects. IC 1011 became its archetype, an example so extreme that it defined the category. Within the Able 2029 cluster, it occupies the gravitational focus around which the rest of the system is organized. Its vast halo is not merely decorative, but structural, linking the galaxy to the cluster through a shared pool of stars and dark matter. In the following decades, deeper imaging continued to reveal new layers of faint light around the galaxy. Each new survey pushed the boundary outward, uncovering streams and asymmetries that hinted at the trajectories of long-absorbed companions. Radio observations showed only weak emissions, confirming that the galaxy was quiescent, devoid of the cold gas needed for new stars or the energetic jets that mark active nuclei. The X-ray glow surrounding it was not produced by the galaxy itself, but by the hot intra-cluster gas confined within the cluster's potential well. This distinction emphasized how intimately IC 1011 and its environment are connected. The galaxy cannot be fully described apart from the cluster. Together, they form a continuum of matter, light, and gravity. The more astronomers observed, the clearer the picture became of IC 1011 as a product of time rather than a momentary formation. Its discovery did not reveal a newly active object, but the culmination of a long process of assembly. It represented what happens when galaxies have merged repeatedly over cosmic epochs, losing individuality but gaining scale. The measurements of its velocity dispersion, the range of speeds at which its stars move, showed values so high that only enormous mass could account for them. The gravitational binding energy implied by these motions confirmed that IC 1011 was among the most massive galaxies ever known. Its existence validated theoretical predictions that galaxy clusters should naturally grow central giants through mergers. What began as a faint smudge on a photographic plate thus became a keystone in understanding cosmic evolution. IC 1011 is not simply large, It marks an end point in the growth of structure. Beyond it, the distinction between galaxy and cluster begins to dissolve, the two merging into one extended system. The galaxy's first identification, therefore, stands as a quiet milestone in astronomical history. The recognition that even in the seemingly empty depths of the universe, gravity can sculpt matter into forms so vast that they challenge the boundaries of comprehension. To the human eye, it remains invisible without assistance. Even the largest amateur telescopes cannot detect its light directly. It exists at the limits of vision, visible only through the mediation of machines. Yet those machines, gathering photons one by one over hours and days, assemble an image that bridges the gulf of a billion years. In that image lies both the past and the present of a galaxy that continues to shape the cluster around it. The same faint glow that first appeared on fragile photographic glass still arrives at Earth, carrying within it the unbroken record of ancient starlight. The galaxy's first glimpse was not an end, but the start of a continuing act of observation, one that quietly expands the scale of what can be known. The outermost regions of IC 1011 extend so far into the cluster that they appear to dissolve into space itself. Here the light is faint, nearly indistinguishable from the background glow of Able 2029, and yet it persists, an endless gradient of brightness that fades too slowly to define a clear edge. This domain is known as the stellar halo, a vast sphere of ghost light surrounding the galaxy. Within it, stars are sparse, separated by distances far greater than those within the central body. Their combined glow is so tenuous that it can only be traced with the most sensitive instruments capable of distinguishing a handful of photons against the noise of the universe. Still, this faint radiance tells of the galaxy's immense reach, the lingering presence of material stripped and scattered over billions of years. The halo is not uniform. It contains subtle ripples and faint arcs, patterns etched by the gravitational memory of long-past collisions. Some of these arcs are remnants of smaller galaxies that once orbited too close, their stars drawn out into thin tidal streams before being absorbed entirely. Others mark shells of debris from larger mergers, where the combined gravity of two massive systems reshaped the distribution of their stars. These features are almost invisible in direct light, but when viewed through long exposures, they reveal a texture to the halo, a record of motion preserved across cosmic time. Each star in this outer realm follows a slow, elongated orbit around the galactic center. Their velocities are guided not by the visible mass alone, but by the dark matter halo that envelops the galaxy and the cluster beyond. The gravitational field here is gentle but pervasive, holding these distant suns in a vast, diffuse equilibrium. Because of this, the halo behaves like a transitional zone between the galaxy and the cluster itself. Its outermost stars are no longer bound entirely to IC 1011, but drift in shared orbits that connect to the greater gravitational well of AA. In effect, the galaxy's halo and the cluster's core overlap, forming a seamless bridge between the two. This continuity makes IC 1011 appear almost infinite, its light merging with the collective glow of the cluster. Astronomers studying its brightness profile find no simple way to separate one from the other. The boundary is not a line, but a gradual blending of light, matter, and motion. The temperature in this region is close to absolute zero, yet the space is not empty. It is filled with thin clouds of ionized gas, ancient dust grains, and the diffuse plasma of the intracluster medium. Radiation from the hot gas farther inside the cluster passes through it, scattering weakly off electrons and adding a faint X-ray shimmer to the background. In visible light, the scene would appear still and colorless, illuminated only by the distant glow of countless red and yellow stars. Each of those stars is a survivor, ancient, metal-rich, and long past the stage of active fusion. Their light is steady but dim, creating an impression not of brilliance but of endurance. This is the light of things that have persisted for most of cosmic history, drifting through the quiet outskirts of an enormous system. Observing such faint regions is a technical challenge. The light from the halo is often fainter than the natural sky brightness of Earth, requiring long exposure times and careful subtraction of background noise. Astronomers use stacked images, combining many hours of observation to isolate the signal from the galaxy's outskirts. In doing so, they uncover structures too subtle for a single frame, ripples, asymmetries, and faint gradients that reveal the true extent of the halo. These measurements show that the halo's brightness declines smoothly with distance, but never quite reaches zero. Even at several million light-years from the center, the light persists, detectable as a statistical excess over the background. This persistence suggests that IC 1011's influence extends beyond its visible boundary, pulling stars and gas into a gravitational field that merges with the cluster's dark matter envelope. In the context of cosmic evolution, the halo represents the fossil record of IC 1011's growth. Every merger that the galaxy has experienced has left behind some trace in this outer region. When smaller galaxies were absorbed, their stars were thrown outward by gravitational tides, populating the halo with debris. Over billions of years, these events smoothed into the faint glow now seen from afar. The process continues even today, as the galaxy draws in new companions from the cluster's crowded center. The accumulation is so gradual that no single epoch can be called its beginning or end. Instead, the halo stands as the visible consequence of continuity, matter drawn, scattered, and reassembled over unthinkable spans of spectroscopic studies of the outer halo reveal low metallicity compared with the inner regions. This indicates that many of its stars originated in smaller, less evolved galaxies that were later assimilated. The composition of these stars acts as a chemical archive, encoding the histories of the systems from which they came. Because these outer stars move more slowly and in less organized patterns, their orbits preserve information about the gravitational field they inhabit. By modeling their motion, astronomers can infer the shape and depth of the galaxy's mass distribution. The results confirm that the luminous matter alone cannot account for the observed velocities. A dominant component of dark matter must extend beyond the visible light, binding the halo together. In this way, the faintest regions of IC 1011 reveal the strongest evidence for the invisible matter that defines its scale. The halo also plays a role in regulating the temperature and density of the intracluster medium. As the galaxy accretes smaller systems, the gravitational energy released by infalling matter is converted into heat, maintaining the surrounding gas at millions of degrees. Shock waves propagate through the plasma, compressing it and preventing it from cooling efficiently. This feedback ensures that the cluster's atmosphere remains hot and stable, suppressing further star formation both within IC 1011 and in nearby galaxies. Thus, the outer halo is not a passive boundary, but a region of exchange where matter and energy circulate between the galaxy and its environment. From a distance, this interplay produces an appearance of calm. The halo glows with a faint diffuse light that changes little over time. There are no clear edges, No dramatic events visible to the eye. Yet beneath this stillness lies continuous motion. Stars orbiting slowly, gas streaming along invisible gradients, and dark matter shaping the entire configuration. The scale of these processes makes them imperceptible on human time scales, but their effects accumulate, maintaining the delicate balance that defines the galaxy's form. The visual impression of the halo challenges the sense of proportion. Its faintness suggests fragility, yet its size makes it the dominant feature of the galaxy. It extends so far that it encompasses volumes of space larger than entire clusters of galaxies elsewhere in the universe. Within it, gravity weakens, but never vanishes, ensuring that every particle remains tied to the whole. The halo, in this sense, is both the limit and the continuation of IC 1011, a region where the concept of the galaxy begins to dissolve into the broader structure of the universe. In the deepest images, the halo appears almost featureless, a smooth wash of gold against the black of space. Yet that apparent simplicity conceals the sum of billions of individual stars, each tracing its path through the gravitational furrow of the cluster. Their combined light forms the faint veil that astronomers call the envelope. To the eye, it seems still, but in reality, it is a slow symphony of motion playing out across cosmic time. The ghost light of IC 1011's outer halo marks the boundary between what can be seen and what must be inferred, the visible trace of gravity's reach across millions of light years. Around the immense body of IC 1011, space is filled with faint structures that trace the history of countless encounters. These are the tidal streams, elongated filaments of stars drawn out by gravity. When smaller galaxies wander too close, they move in slow arcs around the giant, looping through its halo like threads of light, barely visible against the blackness. Each stream is the remnant of a once coherent system, now stretched thin until its stars have become part of the larger whole. Over billions of years, these events have repeated many times, building the enormous mass of IC 1011 through the steady consumption of its companions. The galaxy's present form is the cumulative result of this process, a structure grown layer upon layer by the merging of smaller galaxies into one colossal entity. When a smaller galaxy enters the gravitational field of IC 1011, its motion is altered long before contact. The outermost stars begin to drift away, forming a bridge between the two systems. This bridge stretches and twists as tidal forces increase, while the cores of the galaxies draw closer under mutual attraction. In time, the smaller galaxy is pulled apart completely, its stars scattering into orbits that follow the curvature of the larger one's potential field. What remains is a faint streak, an echo of its original path. These tidal remnants can persist for hundreds of millions of years before being mixed thoroughly into the background of the halo. Even after their light fades beyond detection, their gravitational influence endures, subtly changing the motions of stars throughout the galaxy. Computer simulations have shown that the growth of central galaxies and clusters like Able 2029 is dominated by such interactions. The process is not explosive, but cumulative, driven by the slow settling of galaxies toward the center of the cluster. Each merger adds its stars, gas, and dark matter to the mass of the central giant. In the early universe, when galaxies were smaller and gas was abundant, these collisions were violent events marked by bursts of new star formation. But in the mature environment of a massive cluster, the galaxies involved are old and depleted of gas. Their mergers are quieter, producing little or no new stars. Instead, they contribute to the smooth expansion of the central halo, enriching it with layers of stellar debris. IC 1011's immense size reflects the long continuation of this cycle, extended over cosmic epochs until nearly every nearby system has been drawn into its orbit. The evidence for these past mergers is written into the galaxy's faintest light. Deep images reveal asymmetries, slight deviations from perfect elliptical form that betray the remnants of past collisions. In the outskirts, faint shells and ripples curve outward like the wake of a stone dropped into water. These are density waves formed when stars from an infalling galaxy oscillate through the gravitational field of the host. Over time, the waves lose coherence, but their presence remains a marker of past disturbance. In IC 1011, such features are numerous but subtle, softened by age and distance until they merge into the continuous glow of the halo. This slow process of cannibalism, known to astronomers as galactic accretion, has shaped the evolution of the cluster itself. As smaller galaxies are consumed, their orbits decay, and their mass is added to the central region. The gravitational potential deepens, drawing in more material and reinforcing the dominance of the core. In this way, IC 1011 acts as both a product and an engine of the cluster's growth. Its pull extends across millions of light years, influencing the motion of galaxies far beyond its visible edge. Over time, this mechanism ensures that the largest galaxy grows ever larger, while the surrounding population becomes progressively sparser. The energy released in these mergers contributes to the heating of the intracluster medium. When two galaxies merge, their dark matter halos interact gravitationally, converting orbital motion into thermal energy that warms the surrounding gas. This heating helps maintain the high temperatures observed in the X-ray glow of the cluster. At the same time, the collisions stir the gas, redistributing it through turbulence and shock waves. The result is a delicate balance. While the galaxies themselves grow by accretion, the environment remains too hot and diffuse to allow new galaxies to form. The system has reached a state of equilibrium, where growth comes only through the internal rearrangement of existing matter. The stars that populate the tidal streams of IC 1011 move in complex paths determined by the combined gravity of the galaxy and the cluster. Their orbits are often elongated and inclined, intersecting one another in intricate patterns. Over time, these stars spread out, forming a diffuse halo that becomes indistinguishable from the galaxy's outer envelope. Yet, in certain wavelengths, subtle gradients remain detectable, allowing astronomers to trace their origins. The metallicity of these stars, measured by the relative abundance of heavy elements, often differs from that of the core population. Such differences act as fingerprints, identifying the distinct lineages of the systems that contributed to the galaxy's growth. Through these observations, the history of IC 1011 can be reconstructed not as a single formation event, but as a sequence of merges that span the lifetime of the universe. In this sense, the galaxy's outer regions are less a boundary than an archive. Each faint filament and dispersed cluster of stars preserves information about a former companion. Some of the oldest stars now orbiting in the halo may once have belonged to galaxies that formed soon after the Big Bang. Their continued presence here connects the present structure of IC 1011 to the earlier stages of cosmic evolution. The halo's diffuse light is therefore more than a visual phenomenon. It is a fossil record of gravitational interaction on the grandest scale. From a human perspective, the idea of a galaxy devouring others might seem violent. Yet the time scales involved transform the act into something almost serene. A single merger may unfold over billions of years, so slowly that its progression would be imperceptible within the entire span of human civilization. The absorbed galaxies do not vanish in bursts of destruction, but dissolve gradually, their stars continuing their lives under new gravitational masters. The process is one of continuity rather than end, mass and light redistributed, order redefined. Today, IC 1011 continues to grow. Observations of its surrounding region show faint companions drifting inward, their velocities gradually decreasing as they approach the cluster's core. Each of these will one day contribute to the galaxy's mass, though the process may take longer than the remaining lifetime of the universe, as it is now understood. The scale of time and distance involved renders the galaxy almost eternal in human terms. Its tidal streams and cannibalized companions are the visible evidence of an endless cycle of assembly that has no clear beginning and no final. Against the silence of deep space, these structures shine faintly, too weak for the human eye, yet persistent enough to be captured by instruments that gather their light photon through them. The story of IC 1011's growth becomes visible, not as a single event, but as a continuous act of transformation that has shaped one of the universe's largest and most enduring creations. Within the enormous body of IC 1011, the light that fills its vast interior comes almost entirely from ancient stars. These are populations that formed when the universe itself was young, long before the Milky Way had gathered its spiral arms or the sun had come into being. Their combined glow gives the galaxy its pale golden hue, a color that speaks of time, of stars that have burned steadily for billions of years and now rest in their quiet middle or final stages of evolution. Unlike the blue-white brilliance of youthful galaxies, still rich in gas, IC 1011 shines with the subdued warmth of age. Its light is dominated by long-lived low-mass stars, the survivors of an era when star formation was more vigorous and widespread. Through these stellar remnants, the galaxy preserves a record of the early universe, written in the language of light. Astronomers categorize stars and galaxies by their age and chemical composition, calling these groups stellar populations. In IC 1011, almost all belong to what is known as Population 2, old, metal-poor stars that formed in an epoch when the elements heavier than helium were scarce. Metals, in astronomical terms, are the products of previous generations of stars that have lived and died, enriching their surroundings through supernova explosions. Because the stars of IC 1011 contain relatively few of these heavier elements, they must have been born during an early phase of the universe, when only the first cycles of stellar creation had begun to build the chemical complexity seen in later ages. Their faint red and orange tones reveal this history, a quiet glow that has endured for nearly the entire lifetime of the cosmos. Spectroscopic studies of IC 1011's light confirm this picture. When broken into its component wavelengths, the galaxy's spectrum reveals absorption lines characteristic of old stellar populations. These features, formed by the elements in the outer atmospheres of its stars, show minimal signs of recent chemical enrichment. There are few traces of the cold gas or dust that would signal ongoing star formation. The hydrogen lines that mark regions of new stellar birth are almost absent. This spectral silence indicates that the galaxy has been quiescent for billions of years, with no significant bursts of creation since the distant past. The stars that now shine within it were formed during an earlier, more active cosmic era, and have simply continued their long, steady evolution ever since. In the dense central regions of IC 1011, these old stars are packed together in extraordinary numbers. The gravitational pressure is so great that the average distance between neighboring stars may be only a fraction of that in the Milky Way's disk. Yet, despite this crowded environment, collisions are exceedingly rare, for even at such densities, the space between stars remains vast. The collective gravity of this population produces a smooth, featureless brightness when viewed from afar. Individual stars cannot be resolved. Their light merges into a continuous glow that defines the galaxy's luminous body. The brightness decreases gradually with distance from the center, following a predictable profile known as the de Vaucouleurs law, a pattern characteristic of elliptical galaxies whose stars have settled into a state of dynamic equilibrium. Farther from the core, the density drops and the stars move in more irregular orbits. Here, remnants of past mergers mix with the native population, forming a layered structure of different ages and metallicities. In some regions, faint globular clusters can be detected, ancient spheres of tightly bound stars that predate the formation of the main galaxy itself. These clusters act as fossil witnesses to earlier epochs of assembly. Their orbits trace the gravitational history of IC 1011, looping through its halo as relics of the first structures that merged to create it. Each cluster contains hundreds of thousands of stars, all roughly the same age, glowing faintly with the light of continuity. In such an environment, stellar evolution proceeds at a slow, predictable pace. The most massive stars long ago exhausted their fuel and ended their lives as supernovae, leaving behind neutron stars and black holes that now drift unseen among the living population. The majority of the remaining stars are smaller and more stable, their nuclear fusion balanced and enduring. Many are red giants, old stars swollen in their final phases, casting a steady light that enriches the galaxy's golden tone. Others are main sequence dwarfs, cool and dim, destined to outlast even the memory of their origins. Together, they create a luminous fog that fills the galaxy's volume, shining evenly in every direction. The absence of young stars is one of IC 1011's defining characteristics. Star formation requires cold molecular gas, and in the dense, hot environment of the Able 2029 cluster, such gas cannot survive for long. Any material that might cool and collapse into new stars is quickly heated by the surrounding plasma or stripped away by tidal forces. As a result, the galaxy has aged in near isolation, its stellar population simply growing older as time advances. Observations in infrared and radio wavelength confirm that the reserves of cold gas within IC 1011 are negligible. It is, in effect, a fossil galaxy, one that continues to shine only because of stars born in an era now billions of years gone. Despite its apparent stillness, the internal motions of these stars are complex. They move in random directions, their velocities reflecting the galaxy's enormous mass. Measurements of this velocity dispersion reveal speeds of hundreds of kilometers per second, sufficient to keep the stars bound even against the vast gravitational potential of the cluster. The motions are not chaotic, but statistically statistical, producing a stable spheroidal shape. Within this equilibrium, every star contributes to the galaxy's internal pressure, supporting it against collapse. The interplay between gravity and motion ensures that the system remains dynamically alive, even in the absence of new creation. Some clues suggest that IC 1011 once experienced more active times. In its central regions, faint color gradients hint at slightly younger populations, perhaps formed during the last major merger several billion years ago. When two large galaxies collide, The compression of gas can trigger brief bursts of star formation before the remaining material is exhausted. These intermediate-age stars, though old by human standards, represent the final wave of creation that added to the galaxy's mass. They now blend seamlessly with the older background, leaving only subtle variations in color and metallicity to mark their presence. The collective light of these stellar populations defines IC 1011's identity. It is not a galaxy of dynamic renewal, but of endurance, a system that has reached maturity and remains in a state of quiet stability. Its brightness, when measured across the electromagnetic spectrum, shows no rapid variability or evidence of active processes. Even the region around its likely supermassive black hole is subdued, producing none of the intense emissions that characterize active galactic nuclei. The entire galaxy seems to exist in a phase of equilibrium, where energy flows and gravitational forces balance with exquisite precision. To observe IC 1011 is to witness the outcome of cosmic aging. Every photon that escapes its surface carries the signature of stars that have burned for billions of years without interruption. Their light travels across space as a silent record of persistence, unchanged except for the stretching of its wavelength by the expansion of the universe. When that light reaches Earth, it reveals not a moment of activity, but a sustained presence, a glow that has endured through most of cosmic history. In its faint golden tone lies the quiet truth of a galaxy that has outlived the turbulence of its youth, a stellar population that continues to shine unchanged beneath the deep silence of the cluster that surrounds it. In the vast interior of IC 1011, the calm light of ancient stars drifts through an environment almost entirely devoid of the raw materials from which stars are born. The galaxy's immense body, though brilliant to distant observers, hides a profound emptiness within, an absence of gas and dust that marks the end of its creative life. What remains is a fossil of formation, a monument of matter, long settled into equilibrium. The few traces of gas that persist are relics, thin and heated, suspended in the interstellar void at temperatures so high that they glow faintly in X-rays rather than visible light. These residual elements do not cool or collapse into new stars. They are remnants of what once fueled the galaxy's luminous youth. Over time, the steady rhythm of cosmic evolution has stripped IC 1011 of nearly every ingredient that could renew its stellar population, leaving behind a system defined by light alone. In younger galaxies, gas and dust act as the seeds of creation. Molecular clouds condense, fragment, and collapse under gravity, igniting into clusters of newborn stars. But within the dense, hot environment of the Able 2029 cluster, such clouds cannot survive. The space between galaxies is filled with plasma heated to tens of millions of degrees, a medium so energetic that it prevents cooling on any meaningful timescale. As IC 1011 moves through this environment, its outer layers interact with the surrounding plasma, and the friction between them strips away any remaining gas. This process, known as ram pressure stripping, leaves the galaxy bare. Even material expelled from dying stars, which might otherwise replenish its reserves, is swept into the intracluster medium almost as soon as it is released. In this way, the galaxy's natural recycling process is halted, ensuring that it remains dormant. The dust content of IC 1011 follows the same pattern of decline. Dust grains form in the envelopes of old stars and supernovae, but without new star formation to produce heavier elements. Their supplied infrared observations detect only the faintest traces of warm dust scattered unevenly through the core. These particles absorb a small fraction of the starlight and re-emit it as weak thermal radiation, barely measurable against the cosmic background. Compared to spiral galaxies or star-forming irregulars, IC 1011's dust mass is negligible. Its once dynamic cycles of creation and destruction have given way to stasis, a quiet mence between radiation and gravity. The interstellar medium that remains is thin, hot, and inert, a silent witness to the galaxy's long exhaustion. Even so, small regions of residual activity persist. In the central few thousand light-years, faint signatures of ionized gas suggest that the supermassive black hole at the core may still exert influence on its surroundings. Though it no longer drives the dramatic jets seen in active galaxies, it likely continues to accrete small amounts of matter, perhaps the gas lost by aging stars within the dense core. This process heats the surrounding material, producing soft X-ray emission and maintaining the region's stability. The energy released in this subtle way is enough to prevent cooling, but insufficient to ignite a new era of creation. The result is a delicate equilibrium. The core remains luminous, yet the conditions necessary for new stars never arise. In this state of balance, the galaxy's structure endures almost unchanged. The lack of cold gas means there are no shock fronts, no clouds collapsing under self-gravity, no bursts of ultraviolet light from newborn clusters. Instead, the starlight is constant and uniform, unbroken by regions of brightness or shadow. The interstellar space within the galaxy is nearly transparent. Light from distant stars passes through without distortion, giving the interior a clarity that would be impossible in a dust-rich spiral like the Milky Way. The absence of obscuring material reveals the smooth spheroidal symmetry of IC 1011's inner structure, an uninterrupted gradient of light stretching outward until it fades into the diffuse halo. The loss of gas and dust is not unique to IC 1011, but represents an advanced stage in the life cycle of galaxies within massive clusters. The combined effects of time, environment, and gravity conspire to quench star formation, transforming once active systems into dormant giants. In smaller, isolated galaxies, gas can cool and recycle, fueling new generations of stars. But in environments like Able 2029, where the intra-cluster medium is dense and hot, cooling is suppressed on every scale. The result is a population of galaxies that glow steadily but change little. IC 1011, as the most extreme example, stands at the end point of this process. It is a galaxy that has completed its transformation from a place of birth to a place of preservation. This condition of dormancy extends to the galaxy's outer halo. Observations show no significant reservoirs of neutral hydrogen, the fundamental ingredient for new stars. The small amounts that do exist are either too warm or too diffuse to collapse under gravity. Occasionally, external material may drift in from the surrounding cluster, stripped gas from smaller galaxies or remnants of ancient collisions, but the gravitational heating it experiences upon entry prevents it from cooling. Instead, it merges with the hot plasma already filling the cluster's potential well. Thus, even external sources of replenishment are rendered ineffective. The galaxy remains sealed in a state of near-permanent calm. Despite this apparent stillness, the physical processes governing IC 1011's environment are dynamic in a different sense. The energy balance between its aging stars, the hot gas, and the surrounding medium creates a slow but continuous exchange of heat and motion. As stars evolve, they shed material into space, adding mass to the hot gas component. Supernova remnants expand briefly before dissolving into the ambient medium. Each event contributes a fraction of energy to the system, maintaining the temperature of the intracluster gas and preventing large-scale cooling. Over immense spans of time, these mechanisms preserve the galaxy's equilibrium, holding it steady between collapse and renewal. The faint X-ray emissions detected from the galaxy and its immediate surroundings serve as a visible reminder of this process. The radiation originates from electrons moving at high velocities through the hot plasma, their collisions releasing energy in the form of high-frequency light. These emissions, invisible to human eyes but captured by space-based telescopes, trace the distribution of heat throughout the cluster. The glow is smooth and extended, indicating that the plasma is in a stable state. Its uniformity reflects the lack of turbulence or strong shocks, further evidence that IC 1011 has settled into long-term stability. Within this vast and silent structure, creation persists only in its smallest forms. Individual stars continue to evolve, producing heavy elements in their final stages before releasing them into space. Planetary nebulae form and fade. Supernovae occur at intervals measured in centuries, and compact remnants remain behind. These processes, though minute on the scale of the galaxy, sustain the slow chemical evolution that continues even in dormancy. The materials they produce, however, are too diffuse and too hot to coalesce again. They contribute instead to the gradual enrichment of the surrounding gas, ensuring that every particle of matter carries the memory of countless prior generations. The absence of gas and dust gives IC 1011 its distinctive clarity when observed from afar. Its light is soft, unbroken, and uniform across its vast surface. There are no spiral arms, no dark lanes, no bursts of blue or pink. Only the steady radiance of old stars remains, filtered through the thin plasma that pervades its volume. This quiet simplicity is deceptive, for beneath it lies a story of transformation, a record of creation, long concluded, of energy redistributed and balance achieved. The galaxy's present form represents the final phase of galactic evolution, when gravity and heat reach equilibrium and the cycle of birth and renewal ceases. In IC 1011, matter no longer organizes itself into new forms. It simply endures. The faint traces of gas and dust that remain are the afterglow of creation, drifting endlessly through an environment that will never again give rise to stars. The galaxy's luminous body, sustained by the light of its ancient suns, stands as a monument to processes that once shaped the cosmos, but now have fallen into. Within its boundaries, the drama of formation has given way to a deep and permanent calm, a calm that will persist until even the longest-lived stars fade into the darkness from which they were born. At the center of IC 1011, beneath layers of ancient stars and clouds of hot plasma, lies a region where gravity overwhelms every other force. It is here, in this unseen heart, that a supermassive black hole is believed to reside, a gravitational singularity, billions of times more massive than the Sun. No light escapes from it, yet its presence can be inferred through the motion of the stars that circle around their orbits, measured across time by sensitive instruments, reveal accelerations too great to be explained by visible matter alone. The pattern of these motions, rapid near the center, slower, farther out, betrays the influence of an invisible mass. From such evidence, astronomers deduced that a black hole of staggering scale lies buried within the luminous heart of IC 1011. In most galaxies, the mass of the central black hole correlates with that of the surrounding bulge. In IC 1011, whose stellar mass exceeds that of 1,000 Milky Ways, this relation implies a black hole of exceptional size. Estimates suggest it may contain more than 40 billion solar masses, placing it among the most massive ever theorized. At such magnitude, its event horizon would span a region larger than the orbit of Neptune, an invisible sphere in which space-time itself curves back upon itself. Though it cannot be seen directly, its effects extend far beyond this boundary, shaping the dynamics of everything in its vicinity. The surrounding stars form a dense rotating cusp, whose motion provides the most direct signature of the black hole's existence. Observing this inner region requires precision beyond ordinary instruments. Even with powerful telescopes, the galaxy's distance makes its core appear as a faint point of blended light. To study it, astronomers measure spectral lines that shift minutely due to the Doppler effect as stars move toward and away from view. From these shifts, they reconstruct the distribution of velocity and infer the gravitational potential responsible for it. The results indicate an enormous central mass that cannot be explained by any combination of stars or dark matter. Only a black hole of billions of solar masses fits the dead. Its gravity influences not only the immediate surroundings, but also the largest structure of the galaxy, helping to shape its equilibrium. In the earliest epochs of the universe, such massive black holes likely grew through the merger of smaller ones and the accretion of gas during periods of intense star formation. As galaxies collided and combined, their central black holes would have migrated inward, eventually merging into a single, more massive object. Each such event released vast amounts of gravitational energy, rippling through space as waves too subtle to detect from this distance. Over cosmic time, these merges produced the titanic remnant now hidden at the center of IC 1011. With the exhaustion of cold gas and the cessation of mergers, its growth has slowed nearly to a halt. It endures now as a silent core dominating its region, not through activity, but through sheer mass. Despite its dormancy, the black hole may still exert influence on the surrounding cluster. Residual infalling matter, gas lost by aging stars or drifting dust from the halo, can feed the accretion disk that encircles the event horizon. As this material spirals inward, friction and compression heat it to millions of degrees, causing it to emit X-rays and low-frequency radio waves. These emissions are weak compared to those of active galactic nuclei, but their presence indicates that the black hole has not yet gone completely quiet. It remains a regulator of energy, maintaining the delicate balance that prevents the cooling of gas and the resurgence of star formation. This feedback mechanism ensures the long-term stability of IC 1011, allowing it to remain quiescent while still energetically connected to its surroundings. The gravity of the central black hole also plays a crucial role in organizing the stellar distribution of the core. Stars that venture too close are accelerated to enormous speeds, some flung outward into the halo, others consumed entirely. The threshold where this influence dominates is called the sphere of influence, a region spanning thousands of light years in such massive systems. Within it, stellar orbits become chaotic, shaped more by the black hole's gravity than by mutual interaction. Over time, this gravitational stirring erases any trace of ordered motion, producing the smooth brightness profile that characterizes the core. The absence of distinct rotation in this zone suggests that the black hole's reach has long since isotropized the motion of its stars. Though invisible, the black hole's energy budget is immense, Even small amounts of accreted material can release energy equivalent to the output of millions of stars. Yet, most of this energy escapes as radiation or heat rather than visible light. The galaxy's distance makes it impossible to observe these processes directly, but models predict a faint halo of X-ray emission centered on the core, produced by the slow heating of surrounding gas. The spectrum of this emission matches what is seen in similar central galaxies of rich clusters, supporting the idea that IC 1011's black hole is both vast and active at a low level. The relationship between this black hole and the galaxy around it reflects a broader cosmic principle, coevolution. As galaxies grow through merges and accretion, so do their central black holes. The energy released by accretion influences the rate of star formation, shaping the evolution of the entire system. In the case of IC 1011, this relationship has reached a terminal phase. The black hole's feedback, long ago expelled or heated the last of the cool gas, halting new formation and locking the galaxy into its current state. What remains is a balanced configuration where the mass of the black hole and the distribution of stars are matched in a near-perfect equilibrium of gravity and heat. If one could travel near this core, the transition from the diffuse outer halo to the dense inner regions would be gradual but profound. The density of stars would increase dramatically, and their motion would accelerate until individual orbits blurred into a collective shimmer of light. At the very center, the stars would move so swiftly that their paths would trace invisible ellipses around a point of absolute darkness. Time itself would appear distorted, stretched by the curvature of space-time. Yet from afar, all of this activity reduces to a single point of brilliance, indistinguishable from the rest of the galaxy's glow. The hidden black hole at the heart of IC 1011 is both a relic and a regulator. It no longer consumes matter at a rate that alters its environment, yet its gravity governs the dynamics of the entire core. It represents the ultimate endpoint of collapse, the place where density surpasses comprehension and energy becomes inseparable from curvature. Around it, the galaxy moves in steady rhythm, a vast congregation of stars orbiting in absence. The light of those stars reaches outward across millions of light years, while the darkness at their center holds them in place. This balance between light and gravity defines IC 1011's existence, anchoring the largest known galaxy to the invisible force that sustains it. Deep within the luminous heart of IC 1011, gravity commands every motion. The core of this colossal galaxy is not a solid mass, but a dense fluid swarm of billions of stars, each moving under the collective pull of all the others, and of the supermassive black hole at the center. These stars, invisible as individuals, even through the most powerful telescopes, create together the smooth, bright nucleus seen from afar. Their movement is both random and ordered, forming a complex pattern that maintains the core's stability over billions of years. The density here is extreme. Within a few thousand light years of the center, the combined mass equals that of entire galaxies elsewhere in the universe. Yet the core remains tranquil, its balance sustained by the delicate interplay between motion and attraction. Every star, every cluster, every orbit contributes to the equilibrium that defines this immense structure. In galaxies of such magnitude, the gravitational potential is deep and continuous. The central velocity dispersion, the measure of how rapidly stars move relative to one another, can reach hundreds of kilometers per second. Within this region, the gravitational pull of the central black hole merges seamlessly with that of the surrounding stars, creating a unified field that governs their. Some stars follow near circular paths, while others move along elongated trajectories that carry them close to the center before hurling them outward again. Over time, these orbits intersect and overlap, their directions randomized by the cumulative influence of countless gravitational encounters. The result is a system that appears chaotic in detail but remains steady in the aggregate, a gravitational equilibrium that has endured since the galaxy's formation. The inner structure of IC 1011 reveals a shallow brightness profile, a feature common in giant elliptical galaxies. Rather than increasing sharply toward the center, the light flattens into a broad core where the density of stars changes only gradually. This flatness is thought to result from past merges between massive galaxies. When two galaxies of comparable size collide, their central black holes sink toward the merged nucleus, scattering stars outward through a process known as gravitational slingshot. The energy released in this interaction carves out a region of reduced stellar density, leaving behind the smooth core observed today in IC 1011. The extent of this flattened region suggests multiple such merges in its history, each event adding to the cumulative reshaping of its heart. This dynamic balance extends beyond the visible light. The motions of the stars and gas within the core reveal the underlying distribution of both luminous and dark matter. Spectroscopic observations measure subtle shifts in wavelength as light from moving stars is stretched or compressed by the Doppler effect. By mapping these shifts across the nucleus, astronomers reconstruct a portrait of its internal motion. The data show not a simple rotation, but a mixture of random and ordered velocities, a turbulent but stable sea of motion sustained by gravity alone. Within this field, the influence of the black hole dominates the innermost region, while the combined mass of the stars controls the outer layer. Together, they create a nested structure of forces, each level contributing to the overall cohesion of the galaxy. The gravitational energy stored in IC 1011's core is immense. If it could be converted into light, it would outshine entire clusters. Yet this energy is not lost. It is locked into the motion of stars, into their orbits that trace invisible paths through space. Each orbit carries the record of its past, how the star was captured, perturbed, or ejected during the galaxy's long history of mergers. In the dense inner regions, interactions between stars are rare, but significantly. A close encounter can alter a trajectory enough to send a star on a path that leads it perilously close to the black hole. Their tidal forces stretch and heat it until it is torn apart, its material spiraling inward before vanishing beyond the event horizon. Such events occur infrequently on cosmic timescales, but contribute to the slow feeding of the central singularity. The resulting bursts of radiation fade quickly, leaving the core once again in silence. Outside this immediate sphere of influence, the core's gravitational reach continues to shape the motion of the entire galaxy. The stars of the inner halo respond to the combined pull of the core and the black hole, maintaining a slow collective drift that defines IC 1011's overall form. The galaxy's mass distribution ensures that this drift remains stable, preventing collapse or fragmentation. Every layer of the system, from the bright nucleus to the faint outskirts, moves in resonance with the rest, following patterns set in place billions of years ago. It is a form of cosmic order expressed through motion rather than stillness, an enduring choreography written in gravity's language. At larger scales, the gravitational potential of IC 1011 merges with that of the Able 2029 cluster. The core's immense mass anchors the cluster's center, influencing the orbits of hundreds of surrounding galaxies. Through gravitational lensing, the entire region bends light from even more distant objects, distorting their appearance into arcs and rings. These distortions reveal the distribution of mass with remarkable precision. From them, scientists can deduce that the galaxy's visible stars represent only a small fraction of its total gravitational influence. Most of it resides in dark matter. The dark halo, extending far beyond the limits of visible light, provides the structural framework that stabilizes the galaxy and the cluster alike. Within the core itself, the dark matter density is low compared to that of the stars. Yet, its presence remains essential. It shapes the outer boundary conditions for the stellar motions and determines how the velocity dispersion declines with radius. Without this invisible scaffold, the stars would not remain bound in their observed configuration. The harmony between visible and invisible mass ensures the long-term survival of the structure, maintaining its symmetry against the slow erosion of time. Despite the equilibrium, the core is not static. Over immense timescales, gravitational interactions gradually redistribute energy among the stars. Some gain velocity and drift outward, others lose momentum and sink inward. This process, known as relaxation, proceeds so slowly that it may take longer than the current age of the universe to complete. Yet it ensures that the core remains dynamically alive, evolving in imperceptible increments even as it appears still. The interplay of countless orbits sustains the smooth glow that defines the galaxy's center, a radiance produced not by change, but by the balance of continuous motion. In this equilibrium, gravity serves as both architect and caretaker. It holds the stars in their paths, shapes the velocity field, and preserves the coherence of the galaxy's core against the pull of entropy. No external force intervenes, no new energy enters or escapes except through the faint radiation of starlight. The entire structure exists in self-contained harmony, its dynamics dictated by mass alone. To the eye, it appears serene, a golden heart of uniform brightness. But behind that calm surface, every star moves ceaselessly, following the curved geometry carved by the sum of all others. The core of IC 1011 is therefore not merely the center of a galaxy, but the focal point of gravity on an almost incomprehensible scale. It embodies the culmination of countless interactions, the merges of galaxies, the migrations of black holes, the long settling of stars into ordered chaos. Within its luminous sphere, matter and motion achieve balance, producing a stillness that is only apparent. The true stillness lies not in the absence of movement, but in the perfection of its symmetry, a cosmic equilibrium stained through time, so vast that it exceeds imagination. Throughout IC 1011's enormous expanse, traces of its turbulent past remain hidden in the faint geometry of its starlight. Though the galaxy appears smooth and symmetrical from afar, deep observation reveals subtle distortions, shells, ripples, and arcs faintly etched into the outer regions of its luminous body. These features are the relics of ancient collisions, scars left by the mergers of smaller galaxies that once fell into its gravitational field. Each carries the imprint of motion long concluded, a memory written in light. Over billions of years, the visible evidence of such encounters fade, yet their effects persist in the motions of the stars and in the galaxy's structure itself. To study these remnants is to reconstruct the story of how IC 1011 became the largest known galaxy, assembled not in a single act of creation, but through a sequence of merges and absorptions spanning cosmic history. The collisions that shaped IC 1011 were slow by human measure, but cataclysmic in scale. When two galaxies approach, gravity begins to distort their shapes long before they touch. Their mutual attraction stretches them into elongated forms, pulling stars outward in vast bridges and tails. As they draw closer, these tides grow stronger, rearranging the distribution of matter within each. Gas clouds compressed by the collision once ignited bursts of star formation, though in the dense and depleted environment of Able 2029, such activity has long ceased. The final stage of these encounters ends with coalescence, when the two systems merge into one. The resulting galaxy, after countless orbits and relaxations, settles into a new equilibrium, but never completely forgets its past. The faint arcs visible in IC 1011's outskirts are the frozen aftermath of these events, the starlight of long-vanished companions, now folded into the vastness of the whole. High-resolution imaging of the galaxy's periphery shows diffuse layers of light that do not conform to a single elliptical shape. These concentric ripples, often circular or shell-like, trace the oscillations of stars that were displaced by gravitational shock waves during merge. Each shell represents a wavefront of stars moving in sync, slowly expanding and fading over time. The patterns are delicate, barely perceptible against the dark, yet they reveal how the galaxy absorbed smaller systems and redistributed their material. Computer simulations reproduce these forms, showing that they arise naturally when smaller galaxies are consumed by larger ones. The stars of the smaller system, captured by the dominant gravitational field, oscillate through the new potential, creating ripples that can last for billions of years before dispersing completely. Deeper still, within the galaxy's intermediate regions, streams of stars form faint filaments that twist through the halo. These tidal streams mark the paths once followed by entire galaxies. Their curvature and brightness provide clues about the mass of IC 1011 and the shape of its gravitational potential. In the absence of new star formation, such streams are among the few dynamic features still visible, the last remnants of movement in an otherwise settled system. Observing them allows astronomers to reconstruct the sequence of mergers that built the galaxy. The number and distribution of these structures suggest that IC 1011 has consumed dozens, perhaps hundreds of smaller companions during its lifetime, each leaving behind a contribution of stars and dark matter. The aftermath of these collisions extends beyond the visible light. In X-ray observations, the surrounding intracluster medium shows regions of uneven brightness, subtle temperature variations that trace the energy released during ancient merges. When galaxies collide, their dark matter halos merge as well, releasing gravitational potential energy that heats the surrounding gas. This energy remains trapped within the cluster's gravitational well, contributing to the steady X-ray glow that fills the space around IC 1011. The hot gas, in turn, influences the motion of future infalling galaxies, slowing them and guiding them toward the central giant. Thus, the record of collisions is not only visible in starlight, but also in the diffuse radiation of the cluster's atmosphere. The scars of these past events are also encoded in the galaxy's internal structure. The flattened core, the extended halo, and the smooth gradient of brightness all point to a long history of merges between systems of comparable size. In smaller elliptical galaxies, the light increases sharply toward the center, but in giants like IC 1011, the brightness levels off, forming a broad, diffuse core. This structural feature, known as a depleted core, results from the action of supermassive black holes during merges. When two large galaxies merge, their central black holes sink toward the center of the combined system, orbiting one another in a binary pair. As they spiral inward, their gravitational influence ejects nearby stars, carving out a region of lower density. The eventual coalescence of the black holes leaves behind the broad, shallow core, now seen in IC 1011. Its smoothness is therefore not a sign of calm birth, but the cumulative signature of violence long past. Such processes occur over time scales so vast that they defy direct observation. The formation of a shell may take hundreds of millions of years, while its eventual fading may last for billions more. The collisions themselves, stretching across the ages, blur into continuity. In this sense, IC 1011 represents not a frozen moment, but an extended state of transformation. Each merger has contributed to its current form, layering history upon history until all individual identities have vanished. What remains is the integrated outcome of countless interactions, a system so large and old that its structure now embodies the memory of the universe itself. Even as it absorbs new material, the rate of change within IC 1011 has slowed. The nearby galaxies within Able 2029 are fewer and more distant than in earlier epochs. Most of those that could be captured have already been consumed. The remaining ones orbit too far or too fast to be easily drawn in. Over the next billions of years, only a few small satellites will fall inward, adding imperceptibly to its mass. The galaxy's future mergers will be rare, their signatures, yet the marks of those that came before will persist. Subtle asymmetries in brightness, faint deviations from perfect ellipses, and the long diffuse trails that blend into the background light of the cluster. These relics of past collisions remind observers that even apparent stillness is built upon motion. Every smooth curve in IC 1011's profile, every seamless gradient of light, is the product of immense rearrangement. The galaxy's calm is deceptive. It is the calm that follows completion, the equilibrium reached when energy has been distributed as evenly as possible. Its collisions are over, yet their echoes continue to define its. When astronomers study its faint outer layers, they are looking not only at space, but at time compressed into structure, billions of years condensed into the thin radiance that surrounds the galaxy. The relics of these ancient mergers are faint, but permanent. They will fade slowly, smoothed by gravity and diluted by distance, but they will never entirely. Their light will continue to drift outward, merging with the glow of the surrounding cluster, until even the memory of their shapes becomes indistinguishable from the background of the universe. In that diffuse glow lies the last evidence of creation through destruction, the record of how IC 1011 became what it is, and how gravity over ages beyond reckoning shaped one of the greatest galaxies the cosmos has ever produced. Surrounding the visible form of IC 1011 lies an even greater structure, unseen yet fundamental, its dark matter halo. This vast, invisible sphere extends far beyond the galaxy's luminous edge, enveloping it in a gravitational field that binds together not only its own stars, but much of the Able 20. While the galaxy's light can be traced for millions of light years, the dark matter halo stretches many times farther, an immense transparent architecture of mass that defines the limits of its influence. The stars, the gas, and even the intracluster plasma all move within this framework, responding to the pull of a substance that emits no light and leaves no reflection. Without this hidden structure, IC 1011 could not exist in its present form. Its stars would drift apart, its halo would disperse, and the cluster itself would unravel into the void. Dark matter reveals itself only through gravity. Its presence is inferred from motion, the way stars orbit within the galaxy, the way galaxies move within the cluster, and the way distant light bends as it passes through the region. Measurements of these motions show that the visible matter of IC 1011 accounts for only a small fraction of its total mass. The rest must be something unseen, matter that does not interact with radiation but exerts the same gravitational force as any other mass. In the case of IC 1011, this invisible halo outweighs the luminous stars by an order of magnitude, forming the true skeleton of the galaxy. Its density is highest at the center, where it merges with the stellar core and decreases gradually outward, following a smooth spherical profile that extends beyond any boundary detectable in light. The shape of this dark halo has been deduced through a combination of observation and simulation. By studying the velocity dispersion of stars and the hot gas within the cluster, astronomers can model the gravitational potential that must exist to account for their motion. The data suggests that the halo surrounding IC 1011 is not sharply defined, but continuous with that of the cluster itself. In other words, the galaxy's dark matter merges seamlessly into the larger gravitational well of Able 2029, creating a single massive envelope that holds hundreds of galaxies within its domain. The dark halo thus serves as the bridge between the individual and the collective, linking the galaxy to the cosmic web from which it formed. Within this halo, every particle of luminous matter moves along paths determined by the invisible mass beneath it. The stars of the outer regions follow orbits that are slower and more extended than they would be under the influence of visible matter alone. The intracluster gas, heated by gravitational compression, traces the shape of the underlying halo, filling it like vapor in a vast container. Even the faintest tidal streams and relics of past mergers are shaped by this gravitational landscape, their trajectories molded by the curvature of space defined by dark matter. Through this lens, IC 1011 is not merely a collection of stars, but a phenomenon of geometry, a visible expression of an unseen. The origin of such halos lies in the earliest moments of cosmic history. In the young universe, dark matter began to clump under gravity long before ordinary matter could cool and form stars. These early clumps served as the seeds of galaxies, their gravity drawing in gas that condensed into stars and planets. Over time, smaller halos merged into larger ones, creating a hierarchy of structures that eventually gave rise to systems like IC 1011. The dark matter halo that now surrounds it is therefore not only a present structure, but also a fossil of formation, an unbroken remnant of the universe's first gravitational assembly. Though invisible, the halo can be mapped through gravitational lensing, the bending of light from distant galaxies behind the cluster. Observations show arcs and distortions in the background field, subtle elongations that portray the presence of concentrated mass. By measuring these distortions, astronomers can reconstruct a map of the halo's shape and density. The results for Able 2029, and by extension IC 1011, reveal a smooth, centrally concentrated mass distribution that extends for tens of millions of light years. The precision of these maps confirms that dark matter dominates the region's dynamics, outweighing the combined mass of all visible galaxies and gas. The gravitational power of this halo influences not only the internal stability of IC 1011, but also the fate of its surroundings. Galaxies moving through the cluster feel its pull, slowing and curving in their trajectories. Some are captured entirely, their motion eventually bringing them into the cluster's center, where IC1011 resides. In this way, the dark halo acts as a cosmic net, gathering matter and retaining it within the cluster's bounds. Its presence explains the observed cohesion of the system, the way hundreds of galaxies remain gravitationally bound, despite their vast separations and high velocities. Without dark matter, the cluster would have dispersed long ago, its galaxies flung outward by their own momentum into the emptiness between cosmic filaments. Within the boundaries of IC1011 itself, dark matter also shapes the distribution of visible stars. The smooth decline in brightness from the core outward follows the same mathematical pattern as the dark halo's density curve. This parallel suggests that both components are in equilibrium, balanced through gravitational coupling. Where the halo's density begins to drop, the starlight fades in tandem. The visible and invisible matter together form a self-consistent system, each defining the limits of the other. The galaxy's immense stability, its symmetry, and its endurance over billions of years are all consequences of this balance. Although dark matter cannot be detected directly, its interaction with normal matter has indirect but measurable effects. The gravitational compression of gas within the halo produces the high temperatures observed in X-ray emissions. These temperatures, reaching tens of millions of degrees, provide evidence of the enormous gravitational potential surrounding the galaxy. In the same way, the lensing of background light offers a direct measure of the halo's total mass. Together, these independent observations confirm that IC1011 is held together not by its visible stars, but by an ocean of invisible mass, a structure more fundamental than the light it supports. The existence of this halo also carries implications for the future. As the universe expands and distant galaxies drift farther apart, the gravitational influence of dark matter will continue to bind IC1011 and the while other regions of the cosmos recede beyond the horizon of visibility. The cluster will remain cohesive, isolated within its own gravitational domain. In time, it may become a self-contained island of matter, drifting through an increasingly empty universe. The dark matter halo will preserve its structure long after the stars within have faded, maintaining the shape of the galaxy even in darkness. Thus, the unseen halo is the most enduring part of IC1011. The stars will age, the gas will cool, and the light will eventually dim. But the invisible mass will remain, silently holding its form against the expansion of the cosmos. It is the true body of the galaxy, unseen but omnipresent, a structure made not of atoms but of gravity itself. Through it, the legacy of IC1011 will persist long after its light has faded, a shadow of mass that endures in the great silence between galaxies, a reminder that the universe is built as much from what cannot be seen as from what can. Though IC1011 stars emit the soft golden light of age, the galaxy's true radiance extends far beyond the narrow range visible to human eyes. Across the electromagnetic spectrum, from long radio waves to high-energy X-rays, the galaxy and its cluster release a complex array of signals that together reveal the hidden mechanics of its vast environment. Each wavelength tells a different story, the slow rhythm of charged particles spiraling through magnetic fields, the faint hum of ancient starlight stretched by cosmic expansion, the steady pulse of X-rays from superheated gas bound by gravity's grip. Observing this spectrum is like listening to a symphony where every instrument plays on a time scale of millions of years. It is through these invisible forms of light that astronomers decipher the galaxy's surface, its history, and the forces that sustain its calm. In radio wavelengths, IC1011 and its surrounding cluster reveal the faint whisper of synchrotron emission, radiation produced by electrons moving at nearly the speed of light through magnetic fields. These emissions are diffuse and faint, but they trace the presence of cosmic rays and magnetic turbulence within the cluster's plasma. Unlike the compact radio sources associated with active galaxies, IC1011's signal is extended, forming a soft halo that blends into the cluster background. This emission likely arises from the slow re-acceleration of electrons left over from ancient periods of activity, perhaps from times when the galaxy's central black hole was more energetic. The resulting glow, invisible to ordinary light, outlines the structure of the cluster's magnetic field, showing how energy is distributed throughout its enormous volume. Moving upward in frequency, the infrared spectrum offers a record of the galaxy's stellar population and its faint traces of dust. Most of the emission here comes from the old cool stars that dominate the galaxy's light. Their output peaks at longer wavelengths, producing a soft infrared glow that permeates the galaxy's interior. This radiation provides a census of stellar mass, confirming that IC1011 contains several trillion stars. Infrared instruments also detect minute signals from dust grains warmed by starlight, though these are exceedingly weak. The scarcity of dust and cold gas confirms that the processes of creation have long ended, leaving the infrared sky smooth and unbroken. No bright regions mark the birth of new stars. Only the uniform warmth of ancient light remains. In visible light, the galaxy presents its most familiar face, a luminous ellipse, fading gently into the surrounding cluster. Optical observations define its shape and measure its color, both indicators of its age and metallicity. The golden tone signifies a population of old, evolved stars, with few remaining in their blue, youthful phase. Spectroscopic data in this range allow astronomers to measure the motion of stars through the Doppler effect, revealing the galaxy's gravitational structure. Subtle shifts in wavelength across its surface map the flow of stellar orbits, confirming the presence of the massive core and the smooth transition into the halo. The optical spectrum thus serves as the baseline against which all other wavelengths are compared, the visible anchor of an invisible continuum. Beyond the optical and ultraviolet light, the galaxy is almost silent. Young, hot stars and active nuclei typically dominate this region of the spectrum, but IC1011 shows neither. The absence of ultraviolet emission is one of the clearest indicators of its quiescence. Only a faint background glow remains, produced by old stars in their final stages of evolution, such as horizontal branch and post-asymptotic giant branch stars that briefly emit an ultraviolet before fading into white dwarfs. This weak signal confirms that IC1011 is a system of survivors, not of creators. The ultraviolet quietness reflects not emptiness, but age, the result of billions of years of stellar evolution without renewal. At even higher energies, the X-ray domain reveals the environment that surrounds the galaxy. Here, the cluster glows brightly, not from the stars themselves, but from the hot intracluster gas heated to tens of millions of degrees Celsius. This plasma fills the space between galaxies, emitting X-rays as electrons collide with ions. The brightness of this emission traces the distribution of mass within the cluster, providing a map of its gravitational potential. In the case of AEL 2029, the X-ray brightness peaks precisely at IC1011's location, confirming that the galaxy sits at the bottom of the cluster's gravitational well. The smooth, symmetrical profile of the X-ray glow suggests that the system is in equilibrium, undisturbed by recent mergers. The gas, though hot and energetic, is held in place by the cluster's gravity, radiating energy slowly over cosmic time. The core of IC 1011 contributes faintly to the X-ray spectrum through the gentle activity of its central black hole. Observations detect a small point-like source at its center, consistent with a weakly accreting nucleus. The energy released by this slow inflow of matter helps maintain the temperature of the surrounding gas, preventing it from cooling and condensing into new stars. This process, known as feedback, ensures the galaxy's dormancy. The black hole, though quiescent by human standards, continues to act as a thermostat for the entire system, balancing heating and cooling with exquisite precision. Over billions of years, this balance has kept the galaxy stable, preserving its calm and its golden light. Even more extreme phenomena appear when viewed in gamma rays, though in IC 1011 these emissions are faint and diffuse. Gamma rays originate from the decay of energetic particles and from rare interactions between cosmic rays and the cluster's hot gas. Their detection requires long integration times and sensitive instruments orbiting above Earth's atmosphere. In the few cases where such signals have been measured from clusters like AEL 2029, they suggest a low level of ongoing cosmic ray activity, a background hum of high-energy physics that never fully ceases. These gamma rays mark the upper end of the galaxy's energy spectrum, the final frontier of observation before the silence of space resumes. When all these wavelengths are combined into a single composite view, IC 1011 emerges not as a static object, but as a living system in equilibrium. Radio and X-ray emissions trace the energy of the cluster's plasma. Infrared and optical light reveal the accumulated mass of stars. Ultraviolet silence speaks of age and exhaustion. Together they form a spectral portrait of balance. No single range dominates, yet none is absent. Each contributes to the slow symphony of radiation that defines the galaxy's presence across the cosmos. To translate these signals into understanding requires instruments spread across the spectrum. Radio arrays mapping the invisible fields, optical telescopes charting the light of stars, and orbiting observatories detecting the high-energy glow of gas and particles. Through them, astronomers can see the universe as it truly is, a continuum of energy where every wavelength carries part of the same story. In IC 1011, that story is one of completeness. It has passed through the violent phases of growth and reached the calm of balance, emitting a steady radiance that spans all frequencies. Even in its stillness, energy flows constantly, cycling between matter and radiation, between gravity and light. Across every spectrum, from the longest waves to the shortest, IC 1011 continues to speak in the quiet language of the cosmos. Its light, stretched and scattered by distance, arrives at Earth as a faint whisper of harmony, a message from a galaxy so vast and ancient that its energy has become the rhythm of stillness itself. Far beyond the edges of its luminous body, IC 1011 occupies a position of quiet authority within the universe's largest known structure, the cosmic web. This web is the vast network of filaments, clusters, and voids that defines the shape of the cosmos on its grandest scales. It is made not of light but of gravity, a map drawn by the distribution of dark matter and traced by the galaxies that gather along its strands. Within this immense lattice, clusters like ABEL 2029 sit at the intersections where filaments meet, forming the nodes of a structure that extends for billions of light years in every direction. IC 1011, as the central galaxy of such a node, resides in one of the densest regions of this network. Its immense mass anchors the surrounding cluster and helps shape the gravitational field that connects it to neighboring systems across unimaginable distances. The cosmic web itself is a product of time and gravity. After the Big Bang, small fluctuations in the density of matter grew as the universe expanded. Regions that were slightly denser pulled in more material, forming elongated filaments of dark matter that guided the flow of gas and galaxies. These filaments connect clusters like threads, linking beads, defining the architecture of everything visible. Within these threads, matter streams toward the junctions, feeding the growth of massive clusters such as A. The process continues even now, though at a slower pace, as gravity draws galaxies inward along the filaments, and the cosmic web evolves toward greater isolation. IC 1011's role within this network is both passive and essential. It is the end point of countless journeys, the gravitational basin where the flow of matter finds rest. The scale of this structure is almost beyond comprehension. The distances between major nodes of the cosmic web stretch for hundreds of millions of light years, and yet they remain connected by filaments of faint galaxies and dark matter. Observations from deep sky surveys reveal this network as a three-dimensional tapestry, with bright knots marking clusters like AEL 2029 and dim bridges tracing the filaments that link them. Within this map, IC 1011 appears as a bright center of mass, a gravitational anchor whose influence extends outward through the cluster's dark matter halo and into the surrounding web. Its enormous mass helps maintain the integrity of the local node, balancing the inward pull of gravity with the outward push of cosmic expansion. The relationship between IC 1011 and the cosmic web is mutual. While the galaxy depends on the web for its origin and continued growth, it also contributes to the web's gravitational field. The dark matter within and around it adds to the density contrast that defines the node of AEL 2029, strengthening the filamentary connections that link it to adjacent clusters. In this way, IC 1011 participates in a cosmic feedback loop, drawing in material from its surroundings while also shaping the larger pattern that channels new matter toward it. Over billions of years, such interactions have built the large-scale architecture of the universe, transforming random fluctuations into the intricate structure now observed. Computer simulations of cosmic evolution show how galaxies like IC 1011 form at the centers of these dense nodes. As dark matter collapses under gravity, it pulls in gas that cools and condenses into stars. Smaller halos merge into larger ones, and their galaxies merge as well, creating the giant ellipticals that dominate cluster cores. IC 1011 represents the final product of this process, a galaxy that has absorbed nearly all of the matter in its vicinity and now stands at the intersection of multiple filaments. Its size and luminosity are direct consequences of its position. By existing where the flow of matter converges, it has grown larger than almost any other known galaxy, a natural outcome of cosmic geometry rather than coincidence. From the perspective of cosmic scale, IC 1011 and its cluster occupy a small but significant node within the greater supercluster complex that stretches across the local universe. Nearby clusters are connected by filaments of galaxies that weave through the voids, forming chains of structure that extend for hundreds of millions of light years. These filaments are the highways along which matter travels, slowly feeding the central giants at each intersection. The gravitational relationship between IC 1011 and its neighbors is subtle but persistent. Over immense timescales, the attraction between clusters will gradually draw them together, while the expansion of the universe pulls more distant structures apart. In the far future, only bound systems like Able 2029 will remain visible to one another, isolated islands of matter adrift in darkening space. The energy that flows through this web is not in the form of light, but of motion. Galaxies drift along the filaments like beads on strings, following the contours of the underlying dark matter. Their velocities, though small compared with the speed of light, are enough to shape the evolution of structure on cosmic scales. Within the cluster, these motions translate into a slow inward migration, with smaller galaxies gradually spiraling toward IC 1011's gravitational center. Each merger, each act of accretion adds to the mass of the core and deepens the cluster's potential well, reinforcing the connections that tie it to the surrounding web. The cosmic web also serves as a record of cosmic time. Its structure preserves the imprint of the early universe, the ripples and density that grew into the filaments observed today. By mapping the distribution of galaxies within this web, scientists can trace the expansion history of the cosmos and test the laws of gravity that govern it. In this grand framework, IC 1011 stands as one data point among billions, yet it represents one of the most extreme outcomes of those laws. Its mass, luminosity, and central position make it a natural focal point for understanding how the universe organizes itself across scale. The same gravitational principles that hold its stars together also shape the geometry of the web that surrounds it. When seen from the perspective of the cosmic web, IC 1011's apparent isolation becomes an illusion. It is not an independent entity, but a node within a continuous system connected by invisible filaments that span the universe. The light of its stars, traveling outward across billions of light years, eventually passes through the surrounding gas and dark matter that link it to neighboring clusters. The radiation from its core merges with that of the cluster, and then with the background glow of the universe itself. Every photon that leaves the galaxy participates in the same interconnected field, a continuous exchange of energy and information that defines the cosmic structure. As time advances, the expansion of the universe will stretch these connections. The filaments feeding Able 2029 will thin, and the inflow of matter toward IC 1011 will slow. Eventually, the cluster will become gravitationally self-contained, separated from the rest of the web by the accelerating expansion of space. Yet even then, the galaxy's role as a node will persist, frozen in structure if not in connection. Its dark matter halo and the surrounding galaxies will remain locked in mutual orbit, forming a miniature version of the cosmic web, an internal network sustained by gravity long after the larger one fades from view. In this way, IC 1011 serves as both participant and witness to the architecture of the universe. It reflects the pattern of the whole within a single system, filaments of stars connecting to the core, a halo of invisible mass surrounding the visible light, and a gravitational equilibrium that mirrors the quartic balance beyond. The galaxy's role in the web is not to dominate, but to embody it, to exist as one of its many intersections where the universe gathers itself into order. Through its immense scale and stillness, IC 1011 offers a glimpse into the fabric of the cosmos, the unseen network that holds galaxies, clusters, and light together across the boundless reach of space. The story of IC 1011 is far from over, though its light has already entered a long twilight. The galaxy endures at the center of the Able 2029 cluster, suspended in balance, evolving in ways almost imperceptible over human time. Yet nothing in the universe is truly static. The forces that shaped IC 1011 continue to operate, and its future, like its past, will unfold under the quiet rule of gravity, radiation, and time. In the coming billions of years, the galaxy's fate will follow the slow transformations of the cosmos itself, moving from the era of light into an epoch defined by fading stars and expanding darkness. Though the galaxy now appears eternal, every process within it advances toward a state of deeper stillness. Over the next few billion years, the stars of IC 1011 will continue their steady evolution. The more massive among them, though long past their brightest phases, will end as white dwarfs or collapse into neutron stars and black holes. The less massive stars, which make up most of the population, will shine quietly for trillions of years before their nuclear fuel runs out. Each of these stellar deaths will occur in silence, one by one, until the galaxy's glow begins to dim. Supernovae, once more common in younger epochs, will become rare events. The supply of gas needed for new stars is already gone, so none will rise to replace those that fade. Over immense timescales, the color of IC 1011 will shift further toward red, its light growing weaker and colder, until only the faint glow of dying stars remains. The gravitational balance that now defines the galaxy will persist, but small changes will accumulate. As stars exhaust their energy and shrink into compact remnants, the total luminosity of the galaxy will decline. While its mass remains nearly constant, the distribution of these remnants, white dwarfs, neutron stars, and stellar black holes, will reshape the internal structure subtly, creating a darker and more diffuse interior. Gravitational encounters will continue to scatter stars into new orbits, slowly expanding the galaxy's outer layers. Some stars will gain enough velocity to escape entirely, drifting into the intergalactic. Others will fall inward toward the center, occasionally merging or being captured by the supermassive black hole. These processes are slow beyond comprehension, yet they ensure that even apparent stillness hides motion. The central black hole, already among the largest in existence, will continue to grow, though at a diminishing rate, matter still falling toward the galaxy's core. Stray gas from old stars, compact remnants disturbed by gravitational interactions, or occasional dwarf galaxies captured from the cluster will feed it in small amounts. Each addition will deepen its gravitational field, increasing its mass fractionally over eons. As it consumes more material, the region immediately around it will become emptier, cleared by the same gravity that sustains it. In time, the black hole may come to contain a measurable portion of the galaxy's total mass, a dark heart expanding as the rest of the system fades. Beyond IC 1011 itself, the cluster that surrounds it will also change. The galaxies still orbiting within Able 2029 will continue their slow migrations toward the center, their paths decaying under the drag of gravitational interactions. Over the next tens of billions of years, many of these satellites will be absorbed, merging into the core and adding their stars to IC 1011's halo. The cluster will grow quieter as its population declines, its once crowded field of galaxies reduced to a handful of giants embedded in a common halo of stars. Eventually, nearly all of the cluster's visible light will merge into a single structure, an even larger elliptical galaxy, perhaps several times the mass of IC 1011 as it is known today. In this distant future, Able 2029 may no longer be a cluster at all, but a solitary galaxy surrounded by faint debris. As cosmic expansion continues, the universe beyond will grow more remote. Distant clusters will drift away faster and faster, carried beyond the horizon of visibility. The light they emit will stretch to longer wavelengths until it disappears from view entirely. From within IC 1011, the surrounding cosmos will appear to recede, leaving only the local gravitational domain intact. The dark matter halo that now connects Able 2029 to the wider cosmic web will become isolated, cut off by the accelerating expansion of space. In this isolation, the cluster will become a closed system, its internal gravity the only force holding it together against the emptiness outside. In such a universe, IC 1011 and its descendants will persist as one of the last beacons of structure. The remaining stars will continue to orbit in perfect stillness, each tracing its path through the silent dark. The ambient glow of the intracluster medium will fade as the gas cools, its X-ray radiation weakening until it merges with the cosmic background. Within the galaxy, only faint infrared light from aging stars and the occasional flash of a dying white dwarf will remain. Over even longer spans of time, these too will fade, leaving the galaxy illuminated only by the residual heat of degenerate matter, an invisible whisper of warmth radiating into the cold. Far into the future, when the universe is trillions of years older, the black hole at the center of IC 1011 may dominate what remains. Surrounded by a halo of dark matter, stellar remnants, and wandering planets, it will represent the last concentration of mass in a region where everything else has dispersed. Some of the black holes formed from earlier generations of stars may drift inward and merge with it, adding to its mass. Others will escape into the cluster's outskirts, orbiting in the dim void. The combined gravity of these remnants will preserve the overall structure even as visible light vanishes. IC 1011 will no longer be a galaxy in the sense now understood. It will be a gravitational memory, a pattern of matter frozen into the fabric of space-time. The distant descendants of today's stars, white dwarfs that have cooled to black, neutron stars that spin in silence, planets that have lost their light, will continue to orbit the core, invisible but still bound. Some will fall inward over unimaginable timescales, their collisions producing brief flashes of radiation before vanishing. Others will drift outward, carried by the faint gravitational exchanges that still ripple through the system. The galaxy's shape, though no longer visible, will endure as a configuration of gravity alone, even without light. IC 1011 will remain a silent structure embedded in an ever-darkening universe. Beyond even these times, the physics that govern matter will continue to evolve. The expansion of the universe may stretch space to the point where the remaining particles of radiation lose all energy, leaving the cosmos in near-perfect darkness. Yet within that darkness, the mass of IC 1011 and its cluster will persist unchanged by distance or light. Its black hole, like countless others across the cosmos, will remain as one of the last anchors of existence. Only after unimaginable epochs, periods measured in numbers too large for language, will even those black holes begin to decay through the slow emission of Hawking radiation, releasing their energy back into the fabric of space. When that happens, the galaxy will finally dissolve completely, its matter return to the background from which it came. For now, IC 1011 continues to shine, a monument of cosmic stability. At the center of its cluster, its light travels outward across the expanding universe, a steady echo of creation's earliest energy. Though its future leads toward stillness and its stars toward extinction, its existence remains a testament to gravity's endurance, the quiet persistence of structure in a universe that moves always toward disorder. The galaxy's eventual fate mirrors that of all things, bound by time to fade, to cool, and finally to blend with the vast equilibrium that awaits beyond light. But until that distant silence arrives, IC 1011 will remain a golden remnant of the cosmos at its most complete, holding within its calm the memory of all the collisions, stars, and ages that built it. Beyond IC 1011 and the cluster that holds it lies the unbounded architecture of the cosmos, an expanse so vast that even a galaxy of this size becomes insignificant within it. The visible universe extends for tens of billions of light years in every direction, filled with hundreds of billions of galaxies, each a congregation of stars and dust bound by gravity. Yet, when viewed at the larger scales, all of this light fades into a faint uniform glow. What seems immense from a human perspective is in the cosmic view only one small fragment of a much greater continuum. IC 1011, though one of the largest single galaxies ever observed, is no more than a luminous grain in a sea of others. Beyond its halo, the web of matter continues, its filaments stretching through the cosmic voids toward other clusters, superclusters, and regions where gravity still weaves light into structure. At these scales, the individual identities of galaxies disappear, replaced by patterns of density and motion. Light itself becomes the map by which the universe is understood, a record of its expansion, its age, and its ultimate direction. The galaxies recede from one another as space stretches, and the farther they are, the faster they move away. This motion is not travel through space, but the growth of space itself, an ongoing expansion that began with the Big Bang and has never ceased. The universe, once dense and hot, is now vast and cold, its energy spread thin across incomprehensible distances. IC 1011, sitting quietly in the heart of Able 2029, is both a participant in this expansion and a refuge against it, held together by its own gravity, even as everything beyond it drifts away. In this era, billions of years after the formation of the first stars, the universe has entered a mature phase. Star formation has slowed, and the great cosmic structures have reached their full extent. The filaments of the cosmic web no longer grow thicker. They merely shift, flowing inward toward the massive nodes like AEL 2029. IC 1011 stands at one of these intersections, acting as both recipient and witness to the process that defined cosmic evolution. Around it, the remaining galaxies of the cluster trace slow looping paths through the shared gravitational field. Their orbits will continue for many billions of years more, even as the space between clusters expands beyond communication. The visible universe is already thinning, its brightness diluted by distance, its history carried away on the redshifted light of receding worlds. As the expansion accelerates, driven by the mysterious influence known as dark energy, the fabric of the cosmos will continue to stretch. Over immense timescales, the rate of this expansion will increase until the most distant galaxies move beyond the limit of observation. Their light, stretched to infinite wavelengths, will fade from view. In time, only the nearest clusters, those gravitationally bound like Able 2029, will remain visible to one another. The universe will appear smaller, though it will have grown larger. In that far epoch, observers within IC 1011, should any still exist, will see only their local group of galaxies surrounded by darkness. The cosmic web that once connected everything will have dissolved into invisibility, its filaments stretched beyond the horizon of sight. Yet within this shrinking horizon, life and motion will continue, governed by the same physical laws that shaped the early universe. Gravity will still bind stars to galaxies, galaxies to clusters, and clusters to their central masses. The cosmic background radiation, once brilliant, will cool to near absolute zero, a faint afterglow from the universe's earliest moment. Light will still travel, though ever more slowly, relative to the expanding scale of space. The balance of forces that created IC 1011 will remain, even as the conditions of the universe transform around it. It will persist as a relic of an earlier cosmos, a self-contained system, isolated in the deepening dark. In the far future, when the accelerating expansion isolates every gravitationally bound region, the universe will fragment into countless islands of matter, each drifting alone through an ever-cooling sea. IC 1011 and the Able 2029 cluster will be one such island. The light of other clusters will no longer reach it, and communication across cosmic distances will become impossible. Time will stretch in silence, with only the slow motion of stars and the faint hum of radiation remaining. For all practical purposes, the universe will end, not in fire, but in separation. The vast network of galaxies that once defined the cosmic web will become a collection of isolated shadows, each fading within its own horizon. Even so, the legacy of the larger universe will remain encoded in the structures that survive, the chemical elements forged in the cores of stars, the patterns of gravity recorded in the motions of galaxies, and the faint cosmic background that permeates all space will preserve the memory of what was. IC 1011, like every galaxy, is both a consequence and a record of these processes. Its stars carry the evidence of earlier generations of matter. Its form reflects the logic of the forces that govern all things. Though it will one day vanish from view, it will always have been part of the universal whole, a single note in the vast composition of creation. As the eons pass, the isolation of clusters will deepen, and entropy will continue its slow and inexorable progress. Energy will disperse, temperature differences will equalize, and the universe will approach thermal equilibrium. This is the long decline known as the heat death, when every process that depends on contrast, light against darkness, motion against rest, comes to an end. Long before that moment, galaxies like IC 1011 will fade to invisibility, their stars burned out, their remnants drifting through space as cold embers of matter. Yet, even in that ultimate quiet, gravity will persist as the universe's last architecture, holding its scattered fragments in form long after light has gone. The darkness that follows will not be absolute, but filled with the faintest echoes of what once was. Particles of radiation stretched beyond detection will still carry information about the universe's beginning. The black holes at the centers of galaxies will continue to evaporate through the slow release of energy, their mass converted into the final whisper of light. When the last of them fades, only the fabric of space-time will remain, a vast featureless expanse filled with energy too uniform to form anything new. The universe will not collapse or explode, but settle into an endless stillness, the quiet conclusion of its long evolution. From this perspective, IC 1011 is not merely a galaxy, but a chapter in that story. It represents the height of cosmic organization, the point at which gravity gathered matter into its most complete form. The same laws that built it will also undo it, but its existence, however brief on the cosmic scale, marks a moment of order in an ocean of change. The light that now leaves its stars will continue to travel for billions of years, crossing the expanding void until it is redshifted into oblivion. Long after the galaxy itself is gone, that light will still move outward, carrying the memory of its structure into the dark. Beyond the devourer, the universe continues, vast, silent, and expanding, without end. IC1011 remains a single luminous presence within it, a monument to gravity's patient art and to the passage of cosmic time. The stars within it burn, fade, and die, but their collective light records the history of matter's journey from chaos to order and back again. In the boundless future, when light itself grows cold, the idea of the galaxy will endure, a symbol of the universe's brief moment of brightness, the era when energy found form and form found stillness in the quiet heart of the cosmos. Good night.